Well, hi, this is Bob, and I'm over on page 322, and I tried to stress the importance of learning how to use these standard normal distribution tables throughout my introductory lesson on 6.1, and I thought it would be worth our while, or your while, if I just chose a few of the representative questions. I think they're mostly even ones I've chosen, and work through them, trying to, again, get everybody comfortable with using these tables. And as I tried to explain in the 6.1 lesson itself, in Chapter 7 and Chapter 8, we're going to go back to using formulas again, but in order for us to plug in and use the formula, we're going to have to understand how to find given areas in the z-tables. So it's worth our while to go back and work a few extra questions. And again, I can't stress enough the importance that you feel comfortable using the z-tables. And if there's still some questions that you maybe missed one on a quiz or couldn't understand one on the homework, or you watched my lecture and you checked your solution key, etc., then by all means let me know, and I'll try to, I'll do the best I can to give you some help on it. Anyway, on page 322, the first one I wanted to look at is number 12, and this one, as all of these, I use the term straightforward a lot, but once you know what's happening, the questions really do become more mechanical than thoughtful or analytic. And if there's one thing in the whole course that I can't stress enough, it's the importance of drawing a diagram of the situation. And 12 says we want the area to the right of a z equaling 2.01. Okay, so there's our mean, or our z value of 0, and it doesn't, this may or may not represent 2.01, but that's where I say it is. And so this is the area that we're looking for here. But we know that we can't look up that area directly because our tables, you may recall, are z-tables. For a given z value, they give us the area to the left, not the right. But our strategy is, what we can easily do is we can find all this area to the left of 2.01, and then we simply subtract that area from 1, because we know that the entire area under the graph is like 100%, which is a decimal of like 1 or 1.00, or put as many zeros on it as you like. So I've done the math ahead of time to save problems and going back to the tables and everything. And it turns out that the area, I'm hoping I didn't make a simple copy mistake here, that the area to the left of 2.01 is 0.9778. So for us to find the area to the right of a z of 2.01, we simply go 1 minus 0.9778, and that is equal to 0.222. And that, of course, agrees with the book. Okay, so anytime that you're looking for a z-value, a positive z-value, and the area to the right, and that's normally the, we normally call the area to the right in most situations a tail. We have a right and left tail of the distribution, and whenever we're looking for the area to the right, we simply subtract the area to the left of that value from 1. Okay, and of course you'll have some questions like that. Then the next one I wanted to work out was question number 14. And question number 14 wants the area to the left of z equals negative 0.75. Now this one's what I would consider a gimme. because you may recall that our tables are set up on the left side, that's when z is a negative number, to read the area directly. So all we have to do to find the area to the left of negative 0.75, of course I draw it first, then I go back to my table, I go back to the negative z tables, and I can find this directly, and it turns out to be 0.2266. Okay, so another way to think about this is we're not able directly to find the area to the right of a z-value, a positive z-value, but we are able to find the area to the left of a negative z-value. It sounds kind of wordy, but if you draw the situation, I think that will immediately help. Now, the next question we have, just another type of example. This time it's number 16, and we haven't seen this type of example, well, we'll see it frequently, but here's what we have. We have a z-value of 1.23, and we have another z-value of 1.90, and what we want is the area in between them. You'll see other homework problems like this, of course. So we're looking for that area, and of course, we can't find it directly. Okay, now I can tell you that there's, depending upon your tables, there's probably other ways to find this, but the simplest way to find it is to find the z-value associated with 1.98. That would give us everything to the left going this way. I just drew an arrow to the left there. Okay, so that gives us all the area to the left of 1.98, and it should make sense if we subtract the area to the left of a z-value equaling 1.23. Remember, the area to the left of 1.98 is going to be greater than the area to the left of 1.23, and that difference will indeed be the area that we're looking for. So the area to the left of 1.98 turns out to be 0.9713. And from that, I'm going to subtract the area to the left of a z-value of 1.23, which turns out to be 0.8907. And that difference turns out to be 0.0806. And I'm sure everybody remembers this now, but we can have positive and negative z-values, but area is always positive. Okay, so whenever you're dealing with that situation, this is our approach. Okay, the next one I wanted to take a look at was question 40. And it's a p-value greater, or excuse me, the probability that z is greater than minus 1.43. All right, well, that doesn't tell us much, but as soon as I draw a picture of this, okay, of course, a negative z-value is to the left of our mean there. Remember that the z is, as we'll see in the next section, is associated with the mean. And negative 1.43, I'll say it's right here. But we're looking for the area greater than minus 1.43, which is like saying the area to the right. And our z-table isn't set up for us to find that. Now, there's another way that you could do this, but the simplest way using our table is go to the negative z-table and find out this area here, where I just drew the arrow. That's the complement of the area we're looking for. And it turns out that the area to the left of negative 1.43 is 0.0764. So it should make sense that if we want this entire area here, and that both areas add up to 1, in other words, the 0.0764 is the complement, we could just go 1 minus 0.0764 for our area, and that turns out to be 0.9236. Okay. The next one I wanted to do is number 42. And these are important questions because they asked us to go backwards, okay? Now, they gave us the situation in number 42, but they could have given it to us in words. They could have said, find a z-value that represents the area between z equals 0 and an area of 0.4066. But they did it this way. Here's what this is different now, and we know that the area here is 0.4066. Excuse me. Now, it turns out that with the tables we have, we cannot find that directly. Okay, our table will give us, instead of well, we just can't find it out directly with the tables we have. But in order for us to find the z-value associated with an area to the between 0 and that z-value, we have to remember that our z-tables are going to give us this entire area to the left of our mean, or z equals 0. Okay, and you may recall that where we have the symmetry line there, where our z is equal to 0, or our mean, all right, z equals 0 there also, that this area is exactly 0.5. So although we can't, with the tables we have, look up the z-value for an area between 0 and our missing z that equals 0.4066, by adding 0.5 and 0.4066, I'll throw some placeholders up there. Now we can get a z-value that is going to help us here. Okay, so it turns out that in order for us to use the tables that our book has given us to find out the z-value that represents an area between 0 and our requested z-value, area of 0.4066 again, we have to go into our tables and find either exactly 0.9066 or the closest entry to it. Okay, because that by adding 0.5, it reminds us that the z-value is going to give us all the area to the left of that requested z-value. Okay, again, it sounds kind of wordy, but when you do that, you end up with a z equals 1.32. And of course, I'm hoping that you'll be verifying all of these calculations here, and that this is helpful to make you more comfortable with using our tables. Like anything, it takes some practice. Okay, well, I wanted to do number 47A and number 48A. I'll leave the rest of them for you to look at. And 47A says, find a z-value to the left of the mean so that, okay, let me just, before it gets too wordy here, a z-value to the left of the mean, okay, let's say there's a z-value to the left of the mean, and we want there to be 0.9887 of the area to the right of it. Okay. Remember, we're going backwards now. Instead of going from a Z to an area, we're going an area to a Z. And this area here is supposed to be 0.9887. Now, we know we can't do that directly, okay, because our Z tables aren't set up that way. But what we could do, in other words, we can't go into our tables at 0.9887 to find our Z value. Remember, there are other approaches and other tables, but the way that the book wants us to do this is our Z values would tell us this area right here. Our Z values will tell us the area to the left of that missing Z value there. Okay? So what we're going to do is this is our complement, by the way, of 0.9887. We're going to go 1 minus 0.9887, and that's going to turn out to give us, I didn't write it down, so I better do it real quick on my calculator. .0113. Okay, so now we can go. Now I'll do an entirely new situation here. We've written a comparable problem. This area here is 0.0113, and the Z value associated with that area, the negative Z value, can be looked up now using the negative Z tables. Okay, and the area associated, the Z value, it's negative, of course, because we're on the left side of the graph there, or the symmetry line. The negative Z value associated with an area of 0.0113 turns out to be minus 2.28. I'm going to write our Z value. I keep losing my pen here, so I'm going to take it up to the top of the next page. Okay. And just as a reminder, we knew that the Z value was negative because they told us that it was on the left side of the mean there, or the area that we were looking for was greater than 50%. Okay, and of course the diagram helps us with that. Okay, let's take a look at 48A now. This is just to move around and get a lot of different looks at the Z tables. Find a Z value to the right of the mean. All right, so right away, here's a Z value, and it's got to be to the right of the mean. There's 0. So that 54.78% of the area, I've lost my place here. Find a Z value to the right of the mean so that 0.5478 of the area under the distribution lies to the left of it. Okay. So we're looking for a Z value here, and this is what we're looking for in terms of the area, and that area is 0.5478. Remember, we have to turn those areas from probability or percents back into decimals. Now, this one we can do directly because, again, the way our Z tables are set up. Okay, now my drawing may be way off or it may be pretty close, but what I need to do now, I can do this directly, is go into my positive z tables and find a z that's represented with an area of 0.5478 to its left. Okay, and when we do that, we end up with 0.12. Our missing z is 0.12. I could just write it here for that matter. Okay, so we're just a little bit above the mean there. Okay, so I've got one more example to do here, and it's an odd example, so you can follow it in your solution key. But here's what it says. It says we're going to have a graph, and they want us to find two z-values that are equidistant from our mean. Just write that there again. And the area, in other words, we've got a positive z-value and its opposite. And what we're going to do is this is something that's so important for later. So we're out in what's called the tails now, where the graph is tailing off infinitely in both directions, to the right of the mean and the left of the mean. And what we want to do is and it says that the z-values are equidistant from 0, and since we have symmetry on the graph, that means that the area in each z-value must be the same. And what we're doing, they tell us, is there's 5% of the area is cut up into those tails, equidistant from 0. So we have to divide that 5% by 2, and we end up with 0.025. So what this question is basically saying, and I'm hoping you use your solution key for it to verify, to follow, we want, all we have to do is find one of them, by the way, but this is our situation. It told us to find two z-values, one positive and one negative, that are equidistant from the mean, so that the areas in the two tails add to the following values. And the first one is 5%. So if they're equidistant from the mean, in other words, if this distance equals this distance, keeping in mind we have symmetry on our graph, then that 5%, this represents, of course, the other 95% of the graph, and dividing that 5% into two separate tails means each tail has a 0.025 area. So now the best way to do this would just be to recall that our negative z tables can give us a z-value here directly. And whatever that negative z-value is, its opposite will have to be our positive z-value. And if you go into the tables and find 0.025, an area of 0.025, you'll see that it turns out to be, I'm on the left side now, minus 1.96. And that means that our other z-value has to be positive 1.96. Remember, the graph has symmetry, and the z-values, of course, are going to be opposites of each other. Okay, well, I think that's a good, it's a good run-through of what the different types of questions that you're going to run into on the tables. Again, you've got the numerous book examples, you've got my lecture and my extra homework examples, and the solution key to give you a hand. And, of course, we have our z-tables. So that should be a good foundation for all future questions involving z-values. I'll be back shortly with some thoughts on 6.2. Thank you.